All right, guys, so the number 8 in 12.6 gives you this here. So equals sine y. And it says describe and sketch the surface. Now, for the sketches, I just ask you to do the best you can. And several of you have printed out your own 3D graph paper, the isomorphic graph. That's a remarkably smart thing to do, because it makes even the worst of us look pretty good, right? So if you're just trying to do it on your notebook paper, I'm going to make you do it again if it's not good. Some of you guys can handle that. So what plane am I going to draw a trace in to get started? YZ plane. I love it, because X is not there, which means X can be anything it wants to be. So like somebody over here said, whatever image this is, it's going to repeat it for every value of X. So, I mean, shouldn't have to do any more now. You just draw a sine graph there, right? And then just say that it repeats forever. And you try to, if you get yourself some isomorphic graph paper. So where's the YZ plane here? What's this here? X. There are other ways to do it, but I don't know why you would want to. But you could, as long as you turn that around the right way, you're fine. Right-hand rule has to be followed. So I'm in the YZ plane. So here, if you get yourself some nice graph paper, you can kind of sketch out what it looks like and then just draw lines indicating that it repeats forever. So it's going to be this nifty, like multi-grooved thing in both directions. Is that cool? I mean, you all know what a sine graph looks like. Here's the YZ plane, and then it just goes forever in both directions along the x-axis. You guys cool? Because when is z equal to sine y? For what value of x? Every value of x, because there's no restriction on x. So what is this when x is 3? It's this. I really want this to make sense. So at x equal to 3, what's it going to look like? That. Yes, no, maybe so? Yes, no? All right, that's all I can say about it. Okay. Anything else from homework? Any homework questions? Yes.
What's the name of the equation?
What's the name of it? How do you mean?
Is it like cone or hyperbole or like the name?
It's the infinite waviness. I like that. There's no official name for this. It's not a standard. You know, you're thinking about like in 12.6 we have the paraboloid and the hyperboloid and the one sheet and the two sheets.
Because on the online they want the name of it.
This is the groovy, huh?
On the online they want the name of it. Online over.
Yeah, for example, for the ones 21 through 28, yeah. Now, if it wants the name of it for number 8, that's a little evil for what I just said, right? If that's true, then write in whatever you want to, and then send me respond to your instructor, kind of link through WebDesign, right? And I can take a look and see what the hell it really means. Okay, cool. The infinite waviness, I like that. Or the groovy function. Whatever, grooves. Okay. Anything else from homework stuff? Have you guys gotten into chapter 13 yet? Would be a really good idea to do that. Okay, well, I set up the camera so long for barely anything. Well, let's do a little review. Let's review a little bit. Let's go back a ways to start this review off. Equation of a plane. What do you need for that? The equation of a plane. You can give me that. Say again? Okay. You see, if I said, what do you need for the equation of a line, you wouldn't necessarily say 2 points, even though you're correct, it's still too specific. There are 2 things you always need independent of what they actually tell you. For a line, you need slope and point. I love it. So what do you need for the equation of a plane? Give me one form of the equation of a plane.
A normal vector times r naught.
X naught.
And I hear you over here, right? Normal, dotted with
r naught minus r.
Got it. Right, because what's the normal vector? It's ABC. Right, so these are really the same exact formula. Right? Normal is ABC, dotted with x minus x naught, y minus y naught, z minus z naught. So when you dot that, you get this. So those are the same equation. Right? So whichever way you want to memorize it. This is pretty simple to memorize, hopefully. So whatever situation I give you, if I say find the equation of the plane that does stuff, you got to figure out the normal vector, right? And you got to figure out either a point or some vectors that line that point to points in the plane or something. Right? So normally it's a point and the normal vector that you really want to get. So what trips people up is if I give you 3 points, what would you do? So if I give you... Yeah, so if I say this plane contains the points 1 to negative 2, 4, 3, 5, 1, negative 6, 0, 2. Yeah, I would call like PQR. Yeah. You can do PQ, PR. Sure. It doesn't matter. All you need is 2, right? I like it. Any other vector you create will be a linear combination of 2. I don't know if you guys realize that. Maybe somebody. So like, what's PQ going to be? What would PQ be? PQ, yeah. 2, 7, negative 3. And what would PR be? Gather. Negative 7, 2, negative 2. I like it. Now, let's say, what have I not done? QR. What would QR be? Negative 9? Negative 5? 1. And now what is PR minus PQ? Negative 9, negative 5, 1. Do you see what I'm saying? Do you guys see that? What's PR minus PQ? Negative 9. Negative 5. Of course it is. Any 2 vectors that lie in a plane that aren't parallel will create every other vector in that plane. That's the idea of the XY plane. You tell me some X, you tell me some Y, I can create every point in that plane. Let me let that sink in for a second. Let me say this again. So I got the x-axis and the y-axis. That's all I need to construct every point in the plane. And every point corresponds to a vector that has that as a terminal point. So any 2 vectors that are not parallel, will together create every other vector in that plane. Let me let that sink in. Really, really think about that and why that would make sense. I love their expression. I'm getting all huge range of expressions from people. I like it. Some of you guys are humoring me and going, sure, I got you. Okay. And then how would I get the normal vector from what I've done here? I've done too much here, really. I didn't need to do all I did, but cross any 2 of these.
PQ cross PR.
Beautiful. You could do PQ cross PR. That'll figure out what that is. And then I've got an abundance of freaking points. I can pick any of them and throw that into the equation. But what motivated me to think about doing this is the fact that I know that a plane equation needs a normal vector and a point. Or some way to get what this guy needs, right? This would be weird. If you know these, you know the points they point to. So basically, you know a point. I like it. All right. Where else do I want to go? Oh. Can somebody give me an example of a vector function in R3? What's a vector function? Yeah, cool. A vector function is a function of one variable, very often t, where the result is a vector. It's crazy. So that's why I call it a vector function. The outputs will be vectors themselves. So if I have r of t equals, you said something like this, sine t, cosine t, 4t or whatever. That's a vector function. I like it. Okay. Can somebody give me, now here's comes a weird question that actually is in the homework too. Can somebody tell me a surface that this vector function lies on? Let me help you out a little bit. What component is this? So notice when I want to talk about a curve, which is basically a one-dimensional dude, even if it's twisting around, that means it doesn't cover the surface of something. It's just a 1D thing. It can't cover something. Does that make sense? Very often they will lie on, in fact, they always lie on some kind of surface. So if I say x squared plus y squared equals 1, what kind of surface is that in R3? X squared plus y squared equals 1. Cylinder. I like it. And is that true for this? Is x squared plus y squared equal to 1? Yes, so this guy lies on a cylinder of radius 1. Along the z-axis. I love it. Let me let that sink in. This is the thing, the connection between parametric form and, XYZ form, right? So one surface this guy lies on is x squared plus y squared equals 1. Can somebody give me another surface it lies on? Another surface might be a little bit freaky. How about this? You ready? How about this? You ready? X equals sine of z over 4. Do you see that? What is z? 4t. What's 4t divided by 4? So what's sine of t? X. All right. Now let that sink in. Let that sink in. That's the kind of thing. That's the kind of thing you have to be able to notice. And it's that silly. There are some homework problems that are just like this. Do you understand what I mean when I say silly? That was silly. I mean, what did I do? I just forced z to become t and then put it inside of one of these dudes. So I could also say y equals cosine of
Z over 4.
z over 4, right? Okay. Crazy. Sweet. Maybe. So this vector function, this curve, lies on each of these surfaces. So if I drew these surfaces out, this would lie on it. The points on this are all on these. Okay, maybe. So what about a problem like that in reverse? What do I mean by that? Nah. Let's see. Yeah. Find R of t for the intersection of z equals square root of x squared plus y squared and z equals 1 plus y. Z. So how do I say this? Oh yeah, I love it. So they say find a vector function because you can't say the vector function because there's a lot of different vector functions you could get from this. So let me maybe I could start us off. What's the variable that everything seems to be dependent on? You guys see which one that? Well, z is dependent on x and y, and z is dependent on y. So it looks like everything's dependent on y. I said that variable the most, right? So that's kind of the way I look at this to figure out who to let be t, because I don't necessarily see any nice. Like x squared plus y squared equals 1 would just tell me cosine sine. right, for x and y. Do you guys see that? So you always look for that first. So if I let y be t, what's z? 1 plus t. And then can't I figure out what x is? I mean, that's a very kind of like just heavy-handed brute force approach. Right, so I'm constructing r of t. What does r of t need? It needs x of t. Y of t, well I got y of t. Z of t, well I got z of t. All I'm waiting for now is what x of t is. Yeah, exactly, yeah. You could also put this in there and work with it a little bit to make it look a little bit nicer and then start doing stuff to it. You could also do that. Right? But as a student, it's hard to know, what am I allowed to do? What am I supposed to do is the really good one, right? With this kind of problem, this is the reverse of this in a few different ways. I mean, this one I want to take these and make them parametric functions. I just have to make sure that however I put them together, both of these are true. And that's why it ends up being the intersection of those two. It's all the points where these two are true. How many ways is there to do this? Yeah, in a way, there's an infinite number of ways. There's actually like families of infinity way to do this, but there's an infinite number of ways to do this. And that just makes you feel worse when you get it wrong. You're like, there's an infinite number of right answers, and I got the wrong answers. I can relate to that, don't worry. Okay. What else did I want to tell you? That's the same thing there. Oh, okay. That's all I want to tell you. I think if there's no other specific questions, I just want to let you try this out. This is kind of a review, and then it's like a really, really long ago review. So when I say that, some of you guys get worried, as you should.